Okay. Right. Good morning, ladies and gentlemen. Let's continue with chapter 8, internal forced convection. I think it is about the fourth lecture that we are busy with today. We are not going to finish this lecture today. I think we will finish it by tomorrow. So we have started with an introduction, of course, with this chapter, in which we have looked at where internal forced convection is important. I've shown to you how the velocity distribution and the thermal layers develop, and specifically why we have to get the average mean temperature, and that we cannot just do an integration of the temperatures. We have to take into consideration the velocity at every point, or the mass flow, because that is what's transferring the energy. So getting the Tm value, the mean value, is very important. Then we've looked into closer detail at the entrance region. How do we define the boundary layer and how long it takes before it fully develops hydrodynamically and thermally, and the complications it gives us in terms of the heat transfer coefficients. And then we have started with paragraph 8.4, and I've told you with the previous lecture it's a very important paragraph because in it we are very specifically looking at two very important cases, and these cases are the case of where we have a constant heat flux and the case where we have a constant wall temperature. Now, the constant heat flux is the easier one, and we've already finished it with a previous lecture. And then we've started with the case of the constant surface temperature. Unfortunately, there wasn't enough time for us to finish it. So with the constant surface temperature, that is the surface temperature. In this case, this fluid is being heated. The temperature of the wall is constant. If that's the inlet temperature, then we know that the outlet temperature must obviously be increased because there's heat transfer. However, this path is unknown. With a constant heat flux case, it's a linear line. For this case, it is not linear. Okay. And therefore, we did go and look on a control volume type of approach, and we have derived this equation, and I think we've ended the lecture with approximately that equation. So the ln of this temperature distribution is equal to minus the heat transfer coefficient multiplied by the surface area divided by the mass flow and Cp. However, to do this integration, we've made an assumption. Okay, and the assumption is that this heat transfer coefficient is a constant. And we know it is not a constant. Okay, we know it changes. So we have to take that into consideration. That's a constant, and that is also very constant depending on what the temperature changes. So in general, that is the assumptions that we have made, but we have to remember that one is very important. Okay, so if we now go and solve the outlet temperature from this equation by just doing the E of this, then we get rid of the ln and making it neat, then we can write that the outlet temperature is equal to the surface temperature minus Ts minus Ti e to the minus h As divided by the mass flow rate and the Cp. So this is then for an area with a certain length. So if you now think of this length L, and you've got the diameter, then you can go and calculate that outlet temperature if you've got the average heat transfer coefficient. The question, however, is, yes, okay, that is now great that we can do that, but what would the temperature be here, or what would it be there? Okay, so in this, if you just imagine that this area is obviously dependent on the length of this. If you're going to do it for the same, if this was for 5 meters, you can calculate it, but you can go and do the same calculation just for a 1 meter length. So this area you can write in terms of x. Okay, so therefore we can write this as the mean temperature as a function of x is equal to Ts minus Ti e to the minus h multiplied by the perimeter x divided by the mass flow rate and Cp. And of course, if it is a circular tube, then the perimeter P is equal to pi multiplied by the diameter. So this gives us this equation of the fluid temperature here on the inside. And you can see it's not a linear line. Okay, you can see there we've got the E complication. So typically if you would now go and plot it, you would get a temperature distribution looking something like that. Okay, so this is now Tmx, and let's call that equation 2. Okay, so your equation 2 is describes that line. However, we have to keep on remembering the thing of the heat transfer coefficient, because if we would go and measure the heat transfer coefficient as function of x, it would do something like that. Okay, so if we want to get the temperature at that point there, okay, which would be there typically, then for this path we need to get the average heat transfer coefficient. Somewhere we need to get that average, and if you can get that average accurately, then that point would be accurate. Okay, so the accuracy of this depends on your heat transfer coefficient, which makes it a much more complicated case to handle than the case of the constant heat flux. Now, this is a great equation, and you see it in many books. Okay, people use it, but in many cases they do not really understand the complications of it and what it really means. And you can do this very well by looking at this term here. This term there is known as the NTUs, the number of transfer units. So the number of transfer units in general is equal to the heat transfer coefficient multiplied by the surface area divided by the mass flow rate and the Cp. Okay. And I'm going to come back to that a little bit later about the importance of that equation. But for the moment, if we now have this as a definition, then obviously these two equations can be written as the outlet temperature is equal to the surface temperature minus Ts minus Ti e to the minus NTUs. Okay? And if you now imagine the total length L, the total length of the tube, then you're going to use the total surface area to calculate the outlet temperature. And in this, obviously, you're going to use that surface area there. So the same we can do now with this, for this equation, in terms of the mean temperature as a function of x. We can write it as Ts minus Ti e to the, let's call it minus NTU, and put a small x there. Because the small x tells us now NTU x is equal to the heat transfer coefficient multiplied by Px divided by the mass flow rate Cp. So for any point x. Okay. Okay, now the NTU is very important, and I'm going to get to it just now. But we were actually busy with this thing in terms of getting the good temperature distribution, and we've solved the outlet temperature, but there's something else that is very important in this equation. So if we go back to equation 1, from equation 1, this equation as the lim of Ts minus Te divided by Ts minus Ti is equal to minus the transfer coefficient multiplied by the surface area divided by the mass flow and Cp. Then, taking into consideration that the heat transfer coefficient is equal to the mass flow rate Cp, and let's call that the heat transfer of this fluid, of course. Let's call this F, just to make it clear. Okay, that would obviously be the mass flow rate of the fluid, of course, and the Cp of the fluid. That would actually exactly be the same there. multiplied by the outlet temperature minus the inlet temperature. If we now go and substitute this in there, okay, and make this a little bit neat, and it takes a few steps to make it a little bit neat. It's in the textbook and you can go and do it yourself. Then you can write it that the heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area multiplied by the ln of Ts minus Ti minus Ts minus Te, sorry, not the ln of it, just the area, the heat transfer coefficient multiplied by the area, Ts minus Ti minus Ts minus Ti divided by the ln of Ts minus Ti divided by Ts minus Te. Looks a little bit complicated, but if you just go and put it in and work through it, you're going to get that result. Okay. And this is a very important result because this tells us that the heat transfer rate is equal to the heat transfer coefficient multiplied by the area. And remember what was the problem that we've started with this lecture. The problem was when we've looked at the heat transfer rate here, we've said that we want to say it is equal to a heat transfer coefficient and an area multiplied by a delta T. And the question was, what delta T should we use? Because we know the bulk temperature, that one there, and you can see that if you use that delta T, then most probably it's not going to work that well. And that was the problem that we've started with. So this is now the solution for how you should do it. So it says that the heat transfer rate is equal to the heat transfer coefficient multiplied by the area multiplied by what we call the log mean temperature difference. The log mean temperature difference. Okay, and this log mean temperature difference is equal to Ts minus Ti minus Ts minus Ti divided by the ln of Ts minus Ti divided by the Ts minus Te. We're going to use this a lot. Very important. Okay, so to almost conclude these two approaches that can be followed for constant heat flux and for constant wall temperature, we can summarize by saying this following. Firstly, let's write it like this. For the case of a constant heat flux, okay, the H case, remember H is for constant heat flux. For constant heat flux, we can say that the heat transfer rate is equal to the heat transfer coefficient multiplied by the area multiplied by delta T. And that delta T can be an average delta T between the wall and the fluid. However, for the case where we've got a constant wall temperature, then the heat transfer rate can be written as the heat transfer coefficient multiplied by the area multiplied by the log mean temperature difference. Okay, any questions in terms of the derivation and what the equation means? I'm going to show it to you also, or illustrate it now also with some examples. Okay, so if you're a little bit worried about it, don't be. I'm going to show it to you just now. Right, now coming back to the NTUs. Why is the NTUs so important? It is important from, let's call it a practical experience point of view, and or when you do design work. Okay. We can all do calculations and you can calculate anything that you want, but obviously in practice you want to design things which is going to work and which is going to be of value. Okay. Now let's look at the very simple case of where you've got fluid flowing through a tube, and it's a case where the surface temperature is constant at let's say 100 degrees Celsius, and that is the surface area and that is the heat transfer coefficient. So everything has been given. Okay, and the NTUs, you can go and then calculate the NTUs. So the NTUs is going to be very simply the average heat transfer coefficient multiplied by the surface area. The surface area of the tube is going to be the pi multiplied by the diameter multiplied by the length, divided by the mass flow rate and the Cp of the fluid. And let's look at different possibilities of values for the NTU. Because if you can calculate something, we can get 0 or we can get 1,000,000 or whatever. You can get millions and millions of different NTU values. So if we now have the NTU, remember, we can now say that the outlet temperature is equal to the surface temperature minus the surface temperature minus the inlet temperature multiplied by E to the minus NTU. Okay. And the surface temperature, it's 100, okay? And it's 100. And the inlet temperature we've set is 20. Okay. So for those different cases, we can go and calculate what the outlet temperature will be for different NTU values. Right. So let's suppose the NTU value is equal to 0.01. Then the outlet temperature would be 20.8 degrees Celsius. Therefore, the temperature increased just by 0.8 of a degree Celsius with a wall at 100 degrees. So, what is our conclusion? Not much changed, isn't it? Okay? So let's make it a little bit larger, 0.5. At 0.5, the outlet temperature would be 51.5. Okay. For you as an engineer, if you've got a problem like this where you want to heat something and you've got a source at 100 degrees, you would like to get it close to 100, isn't it? Okay. If it is 1, then the outlet temperature would be 70.6 degrees Celsius. So we're making progress. Okay. If it is equal to 5, then the outlet temperature will be 99.5 degrees Celsius. 99.5. If it is 10, the outlet temperature would be 100. Okay? So what conclusion can we make from that? What conclusion can we make from that? The NTUs, when you start doing your calculations, don't just go and calculate the outlet temperature. Don't just put in the values and calculate it. Get the NTU, because the NTU is going to tell you a lot, even before you do all the calculations. So if you do design work now, what NTU will you choose? Will you choose 10? Yeah, well, at 10 you're going to get to 100 degrees Celsius. You're going to get to heat the water to 100 degrees Celsius. However, remember that the NTUs has to do with area. Okay, so it has to do with the length of the material that you're using or the length of your heat exchanger. So it costs money. Okay, so you can go and make the NTUs 100 or whatever, or 1,000. But the reality is between 10 and 1,000, nothing is going to happen anymore, firstly. And then secondly, if you look at, let's look at NTUs of 3, if you go and check it for 3, then you'll get an outlet temperature of 99.2. Okay? So, a good rule of thumb that I use, and not everybody uses this, it is an NTU of 3. Is sort of the maximum where you want to go. Okay. Because from 3 to 5, you'll have to double the length. And by doubling the length, you're just going to increase the water temperature by 0.3 of a degree Celsius. So it's not worth it. It's going to be too costly, normally. So, if you do design calculations and you do the NTUs, the first thing is if the NTUs is very low, you must know almost nothing is going to happen. And then the second thing is try to limit it to 3. If you get to 3, you know that a lot is going to happen. But after 3, you're just wasting material. Okay, so very important thing that you can maybe try to remember. Right, now let's look at the case, an example. And this example is now for a fluid at 15 degrees Celsius, and the fluid is water, and the mass flow rate of the fluid is 0.3 kilograms per second. And here on the outside we've got condensing steam. And it says the condensing steam is at 120 degrees Celsius. Okay. And the problem is that we want to heat this water to 115 degrees Celsius. Okay? Is it possible to heat water to temperatures higher than 100 and still be a liquid? The answer is yes, if the pressure is high enough. Okay? So in this case, it stays water. There's no phase change of the water on the inside. It is a single phase fluid. Okay? And it is given to us that the average heat transfer coefficient is equal to 800 watts per square meter degree Celsius, and the tube diameter is 25. And the question is, what length of tube is required to get to that temperature of 115 degrees Celsius? Okay. So we have water at the inner temperature of 15, mass flow rate of 0.3 kilograms per second. The average heat transfer coefficient of the water, it stays being a liquid, is 800 watts per square meter degree Celsius. Tube diameter is 25, and they ask us what is the length of the tube that will be needed to get to that temperature of 150. Right, so let's look at the properties of water. Properties of water. Now the water temperature here is 15, it's going to increase to 115. The mass flow rate is given, but the CP values and all the other values are not given. So the question that many of you always have is, well, if I get the properties at what property, at what temperature should I get it? And the answer is normally the bulk temperature. So in this case, we can calculate the bulk temperature. The bulk temperature is 115 plus 15 divided by 2, and that is equal to 65 degrees Celsius. Okay. Now at 65 degrees Celsius, the CP value of water is equal to 4187 joules per kilogram Kelvin. And you can get that from table A9. Okay. Now in this case, the outlet temperature has been given. And then the other question that students then have is, but I don't have the outlet temperature, how do I get the bulk temperature? Well, you can do one of two things. You can choose a bulk temperature just by estimating it. Okay? You can go and make your own estimate, or you can choose that value. Okay? You can go through all the calculations, get the temperature, recalculate the bulk temperature, go and get all the properties and just do the calculation again. In most cases, you'll see that it doesn't change the result with a lot. Okay. But we will also do examples like that. So, if we now look at this problem, then because we have the outlet temperature, we can say that the heat transfer rate to the water is equal to the mass flow rate Cp multiplied by the outlet temperature minus the inlet temperature. And the mass flow rate of the water is 0.3. The CP is 4187. Okay. The outlet temperature is 115 and the inlet temperature is 15. So the heat transfer rate that will occur will be 125.6 kilowatts. Okay. Please, in the test and exam, do not write me an answer of 125,625.53348, whatever watts. It's not an engineering answer. Please make it practical in terms of kilowatts, megawatts, or whatever. Okay, so now we've got the heat transfer rate. So calculating the area is very easy. We can just say that the heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area multiplied by Ts minus Tb, the bulk temperature. Okay, so the heat transfer rate is 125.6 kilowatts, equal to the average heat transfer coefficient has been given as 800. Multiplied by the surface area is pi multiplied by the diameter multiplied by the length divided by the surface temperature. The surface temperature is 120. Okay. Coming back to the surface temperature, because we've got condensing steam on the outside, a fluid that is condensing, evaporating, changing phase has very high heat transfer coefficients in the orders of 10, 20, 30,000, while single phase fluids normally in hundreds. So this resistance to heat transfer is very small. So for all practical purposes, that temperature Ts will be constant. Okay. So it is 120 minus the bulk temperature, and the bulk temperature is 65. So it is very easy for us to calculate the length as 36 meters. You agree? All agree? I'm thankful to see this. There are a few of you shaking your heads because I'm working so hard explaining to you that remember, if we've got a case where we have a constant wall temperature, the T case, then you cannot use delta T. You have to use the LMTD, the log mean temperature difference approach. Okay? So this is incorrect. Okay? It's incorrect. What we should have done is saying that we need to calculate the LMTD. Okay. Now the LMTD might look complicated to you, but I'm going to show to you how easy it is. And I would always recommend that you draw a sketch. Okay. So in terms of this sketch, your wall temperature is 120. It stays constant. Okay? Your inlet temperature is 15 and the outlet temperature is 115. Okay. So the LMTD is, and maybe you must first stop writing and look, and then I will give you an opportunity afterwards to write. Okay. The first thing is the LMTD is this temperature difference. Do you see? 120 minus 15. Now don't write. 120 minus 15. That temperature difference. Okay. Minus this temperature difference. Minus 120 minus 115. So let me make them in pink. So it's that temperature difference. You see how easy it is? And that temperature difference. 120 minus 15 divided by 120 minus 115 divided by the ln of those two exact terms. That term, which is the first one here, 120 minus 15 divided by 120 minus 115. Okay, now you can write it down. Okay, so it's very easy. This temperature minus that temperature divided by the ln of that temperature divided by that temperature. And if you can do the calculation, it is equal to 32.87 degrees Celsius. If we now go and redo the calculation the correct way, then the heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area multiplied by the LMTD. Okay. The heat transfer rate we have determined is 125.6 kilowatts. It's equal to the heat transfer coefficient, which is equal to 800 multiplied by the surface area pi multiplied by the diameter, which is 25 millimeters, multiplied by the length, that would give us the surface area, and multiplied by the LMTD, which is 32.87 degrees Celsius. So the result is, the correct result is 61 meters. Look at the difference. Okay. So the error would have been more than 40%, 46% error, if you do it like this. So it's much longer. So to fundamentally understand it, let me show you typically now what is the thing, and that is that the change in temperature is not like in the case of a constant heat flux, so it doesn't follow this line. So that is the temperature of the bulk temperature that we've calculated as 65. Okay. Now the LMTD gives us for this path, and we do not know the exact points. For that path, it would now go and integrate this area, that area there, and get the average of it. Okay, and that average is, let's suppose it is approximately there. That distance there is the LMTD. Okay? It is also not that point there. So that is not the LMTD. So it doesn't give us the temperature difference halfway through the tube. It gives us the average of the integration. Do you follow? You all look so worried. Not? Yes, question.
So couldn't you just use the pressure for NTU and the reluctant for NTU to calculate the electric?
Yes, you could also do it like that. Let me just see. Yes, exactly. You can also do it like that. So you could have used this equation like this one, because you've got the outlet temperature, you've got the inlet temperature, you can go and calculate the NTU, and from the NTU is that exactly. So you could have done it like that also, yeah. Okay. Okay. Right, the next paragraph in the textbook is paragraph 8.5, and that is laminar flow in tubes. Okay, laminar flow. So paragraph 8.5 is laminar flow, paragraph 8.6 is turbulent flow, and then we are finished with this chapter. Okay. Now, the thing with laminar flow, as I've explained to you many times, or all flow as a matter of fact, Nusselt number as a function of x. If we see how the flow is being heated or cooled, then there's a certain length which is called the LT length. It's equal to 0.05 multiplied by the Reynolds multiplied by the diameter and Prandtl number. Okay, so remember LT is equal to 0.05 multiplied by the Reynolds, the diameter, and the Prandtl number. Now, take note, a circular tube. For a circular tube, there's a very important derivation in your textbook. Please go through it yourself. It's not complicated. Because of time limitations, I'm not going to get to it. But that derivation is now for laminar flow. And because from fluid mechanics, you know exactly what the velocity profile would be, you can go and calculate what the Nusselt number will be for laminar flow. And you can do it take note, for fully developed flow. So for fully developed flow, you can go and calculate it, and the derivation is in your textbook. And it says that the Nusselt number is equal to 4.36. And that is the H case. So it's for the constant heat flux case. Okay. So the Nusselt number for laminar flow, fully developed, is 4.36. And about anybody who passed heat transfer will tell you that. So it's an important number to remember, if you want to remember it. Okay. Then, not given in the textbook, but that derivation is also available in literature. You can go and also derive it for a constant wall temperature. So for constant wall temperature, the Nusselt number is equal to 3.66. Remember, for fully developed flow. And take note, this would be without natural convection. Because the natural convection we are going to add and put in the next chapter. As a matter of fact, in a lab, it is very difficult to get this Nusselt number, 4.36. Why? Because of the natural convection. The moment you do the heating, there's temperature differences, there's buoyancy effects, and you start getting secondary flow. Okay. So it's very difficult to get that, but you can get very close to that. Okay. Now, this is for a circular tube, so many of you would like to ask me, well, what if my tube geometry is different than that of a circular tube? Well, there are two approaches that you can use. Firstly, as we've already discussed, you can go and calculate the hydraulic diameter. It's not always exact, but it's close. But there are also equations available for other geometries. So, for example, in your textbook, in table 8.1, table 8.1, it would give you, for geometries like the circular one, it would give you for a rectangle, for an ellipse, and for a triangle. Okay. And if that is the distance A and that is the distance B, then depending on these values, the Nusselt numbers and friction factors actually changes. So, in the table, it would give you for the circular tube, for Nusselt number, for the constant temperature case, the Nusselt number would be 3.66. It would also give you the Nusselt number for constant heat flux is equal to 4.36. And then it would give you the friction factor is 64 divided by the Reynolds number. Okay. For constant wall temperature, 3.66 as indicated there. For constant heat flux, 4.66. And then the friction factor is 64 divided by the Reynolds number. Okay. And then for an ellipse, just as an example, for the case where A divided by B is equal to 16. Okay, for that case, for example, the Nusselt number T would be equal to 3.65. The Nusselt number H would be equal to 5.18. And the friction factor would be equal to 78.16 divided by the Reynolds number. Okay. So there are tables available in which you can get more accurate results. Take note, that the table in the textbook is not everything that is available there. So lots of more information is available. It just gives you some of the most important ones. So if you have another type of geometry, you will have to go and search for those values. Okay. Now take note, table 8.1 is very important for fully developed. And sometimes people miss these small things in the printing. So this is for fully developed. So table 8.1 is valid for that region where the flow is fully developed. Now your question would be, okay, that's now fantastic that you give me this information, but where do I get the information for this? Some of it is available in your textbook. For example, there's the Equites equation. Now in your textbook, the Equites equation is given as, and I've shown it to you with a previous lecture, 3.66 plus 0.065 multiplied by d divided by L multiplied by Reynolds Prandtl and divided by 1 plus 0.04 multiplied by d divided by L Reynolds Prandtl to the 2/3. Okay, so that's the Equites equation. Now what is very important with the Equites equation, you can see it's got this value of 3.66 plus something. So if the length is small, then this effect becomes larger. Okay, so this becomes then larger, that term. But as the length becomes longer and longer, you will see that this effect becomes smaller. So you can see it in the equation. What is important again, if you look at these equations and you read it, you have to read very carefully for what Nusselt number it is. So this, in this case, it would give you, let's suppose, there is LT. Okay. And you are interested in a tube length like that. So there's your tube. And the tube is exactly LT in length. Okay. Okay, then you know that the heat transfer coefficient is going to do something like that, and there it is going to taper off. It's going to be a constant. Okay. So this equation gives you the integrated average of that heat transfer coefficient, which is very useful. So it gives you that value, the average. Okay. Now your question is, what if it is longer? Well, if it is longer, then this equation is also very nice in that regard. So if your tube is longer, like that, okay, then the equation would do that, of course, and now it would be a constant. And again, if that is the length L that you've used in the equation, it would give you that average there. So it would give you the full average every time. Okay. So it means that it's a very practical equation. Depending on the length, you can just put it into the equation and it will give you the average heat transfer coefficient for that length. Okay. If you now go and look in your textbook and you say, right, now great, now I know this, I know that, and I know this, so this equation is there, where's that equation? Then you'll be disappointed. It's not in your textbook. Okay. Why? Because the solution for that is not, at the moment, there's not a general equation that can be used very widely. Okay. There are solutions for it. It's very complicated, and you can go and get it in literature and textbooks. And just many of those solutions, the calculations of those Nusselt numbers will take thousands of code lines just to get the Nusselt number. But one that I've picked up recently that you can use is the following equation. I think it's the Shaw equation, and it gives the Nusselt number as the following: 1.953 multiplied by the Reynolds, the Prandtl d divided by x to the half, and 4 0.364 plus 0.072 multiplied by the Reynolds number, the Prandtl number, d divided by x, and those two equations are valid for different ranges. The first one for the Reynolds multiplied by Prandtl multiplied by d divided by x, if that is larger than 33.3, and if it is smaller than 33.3, then you use the other equation. Okay. So this is the equation for constant heat flux. Therefore, take note, I'm putting in the H there, and let's just put in the T there in that equation there, so that we can distinguish them from each other. There's a very important difference between these two equations, except for the fact that this is for constant heat flux and that is for constant wall temperature. And the change is, the difference is, here we work with x. Okay. So in this case, this equation, in terms of the developing part, it would give you a local value at one specific point. It doesn't give you the average over a length. Okay. So if this is the length of your tube, you will have to go and calculate it from 0 to L, and then you will have to go and integrate it to get the average of the length. Okay, so the equation is not that friendly, but at least there is an equation. I do not expect of you to use it, but just take note of it so that you can really understand how everything comes together. Right, ladies and gentlemen, there's a problem that I want to do with oil in a pipeline, but we are running out of time. So thank you very much. That is then the end of the lecture.